In the last video, we introduced a powerful logic called predicate logic. And we also talk about how to represent predicate logic and introduced two quantifiers, universal quantifier and existential quantifier. In this video, I'm going to talk about how to do the translating between statements and logical expressions. Let's look at the first example. The statement is, every parrot is beautiful. And before we do the translation, we should first specify the domain. A domain gives you a context. It tells you what X is by default. Here, X is the variable we are going to use. However, know that you can use any letter as the variable. Let's assume if the domain consists of all parrots, then X is a parrot by default. Therefore, you don't have to specify what X is. You only need to introduce a notation to represent X is beautiful. Here, we use Bx to denote this property. So Bx denotes X is beautiful. Then we need to identify the quantifier we should use. Because in the statement, you can see there's this keyword every. Therefore, we should use universal quantifier. So the logical expression should be for any X, Bx. If we assume the domain consists of all animals, we should first introduce a predicate to describe what X is. Then we need to introduce another predicate to describe X property. So we introduce two letters. Px denote that X is a parrot. Then we use Bx to denote X is beautiful. Now, the logical expression should be for any X, if Px, then Bx. Some of you may ask, can we use for any X, Px and Bx? Because it reads naturally, it says X is parrot and X is beautiful. That, unfortunately, is not a correct translation. Because what it says is, for any animal, X is a parrot, and X is beautiful. In other words, it says all the animals are beautiful parrots. Obviously, you can see it's not the same as the original statement. Next one. The statement is, there exists a beautiful parrot. How do we do translation? Again, we should first specify the domain. So you have two options. One, you assume the domain consists of all parrots. And the other one is you assume the domain consists of all animals. So if the domain consists of all parrots, then by default, the variable you choose to represent a number is a parrot by default. Therefore, we only need to introduce a letter to represent X is beautiful. So the logical expression is, there is an X such that Bx. If you assume the domain consists of all animals, just like the previous one, we need two predicates, Px, Bx. Then the translation is, there exists an X such that Px and Bx. Some of you may ask, why don't we say there exists an X if Px, then Bx? But if you think about it, this translation is not a correct one. Why is that? Remember, we want to translate the original statement into a logical expression. Therefore, the original statement and the logical expression should have the same truth value. If you think this implication is the correct translation, now consider, what if in reality, none of the parrots is beautiful? What would be the truth value for the original statement? It would be false, correct? Now, what about the translated logical expression? Is it true or false? If you recall from the previous video, to decide whether this logical expression is true or false, we need to first see which quantifier is used. Here is existential quantifier. Therefore, in order to show this one is true, we only need to find one element in the domain which makes the implication true. Then the whole logical expression is true, right? Now, because it's an implication, we know based on the truth table of implication, as long as the hypothesis Px is false, the whole implication would be true. Therefore, if X is not a parrot, then Px is false. Then this whole implication is true. Then the logical expression is true as well. You can see, even though the original statement is false, according to our assumed real-world scenario, but the logical expression is true. Therefore, this is not a correct translation of the original statement. Next, let's see another example. Here, the question is asked differently. In the question, the predicates are given. Px denotes X speaks Russian. Qx denotes X knows the computer language C++. Also, the domain has been specified. The domain consists of all Mainz students. Now let's see how to translate 4 English statements into logical expressions. The first one is, there is a student at Mainz who speaks Russian and knows C++. To translate this, since the domain has been given, we need to first identify the quantifier. There is this keyword there is, so we should use existential quantifier. Then we have X speaks Russian and X knows C++. Second one, again, we need to identify the quantifier first, which is existential quantifier as well. Then it says X speaks Russian, but does not know C++. Next one. Every student at Mainz either speaks Russian or knows C++. Here, since it says every student, we should use universal quantifier. Then it says either X speaks Russian or knows C++. Last one. No student at Mainz speaks Russian or knows C++. Here, what should we use? In order to decide the quantifier, let's first reword this statement a little bit. It's basically saying for every Mainz student, the student does not speak Russian and does not know C++. Correct? Therefore, we can say for any X, X does not speak Russian, and X does not know C++. There's also another way to translate this statement. Think about this. Isn't that the same as saying there does not exist a Mayan student who speaks Russian or knows C++, right? So let's first translate the sentence that there exists a Mayan student who speaks Russian or knows C++. And we put does not exist there. So both translations are correct. Here are some exercises. I recommend you work on them after watching the video. For all the previous examples, we have only used one quantifier, but sometimes it may be necessary to use more than one quantifier. For example, this one. Every real number has its corresponding negative. And let's assume the domain consists of all real numbers. So how do we translate it? Well, let's try to understand what corresponding negative means. Mathematically, if a number x has its corresponding negative y, it means x plus y equals 0. Now let's reword this statement so we can decide how to translate it. Equivalently, it says, for every real number, there exists another real number such that x plus y equals 0. Once I reword this statement, you can see it involves two variables, and you need two quantifiers. So we introduce pxy to denote this relation that x plus y equals 0. Then we can write this statement as this way. It says, for any real number x, there exists a real number y such that x plus y equals 0. Another example. There is a person who loves everybody. Assume that the domain consists of all people. Let's first try to reword this statement to better see how to translate this statement into logical expression. Equivalently, it says, there exists a person, x. For any person y, x loves y. Now you can see we should introduce a predicate that involves two variables. So we use LXY to denote x loves y. What about quantifiers? Based on my rewording, we know that for variable x, we should use existential quantifier. And for variable y, we should use universal quantifier. So the correct translation should be, there exists a person x. For any person y, x loves y. Now we know when we translate an English statement into a logical expression, sometimes it's necessary to use multiple quantifiers. But then the question is, when you write the logical expression, does the order of the quantifiers matter? The answer is, when the quantifiers are of the same type, the order does not matter. Let's see one example. Assume that the domain consists of all real numbers. Let pxy denote x plus y equals y plus x. This logical expression represents for every real number x, for every real number y, x plus y equals y plus x. And if you swap the order of these two quantifiers, it becomes for every real number y, for every real number x, x plus y equals y plus x. And you can see these two have the same meaning. What if the quantifiers are different? It turns out the order does matter now. Why? Let's see one example. Again, assume the domain consists of all real numbers. And let qxy denote x plus y equals 0. Now, for this logical expression, it represents for every real number x, there exists a real number y such that x plus y equals 0. Let's swap the positions of these two. We have this one. But this one means there is a real number y such that for every real number x, x plus y equals 0. Do they have the same meaning now? Let's check. For the first one, you can see this statement is true, right? Because for every real number x, if you just put a negative sign in front of x, that's your real number y. So x plus y is 0. But this one, it says there is a real number y such that for every real number x, x plus y equals 0. You cannot find such a real number y to make this true. Therefore, this one is false. So you can see these two, after you swap the positions of the quantifiers, they even have different truth values. Now let's see another example, which involves 3 variables. Assume the domain consists of all real numbers. Qxyz denotes x plus y equals z. And you have 2 logical expressions. The order of the quantifiers are slightly different. You can see exists z here, exists z here. Are they the same? You can pause the video and think about it. In order to check that, let's check the truth values of the logical expressions. The first one says, for any real number x, for any real number y, there exists a real number z such that x plus y equals z. You can always find such a number z, right? So this is correct. This is true. What about the second one? This one says there exists a real number z, and for any real number x, for any real number y, x plus y equals z. Are you able to find such a number z? No, you cannot. Because no matter what number z you find, you cannot guarantee for any number of x, any number z, any number y, x plus y equals z. Therefore, these two are not the same. To summarize, if the quantifiers are of the same type, the order of the quantifiers does not matter. If they are different, the order does matter. The meaning of the logical expressions are different.